Last section that we're going to look at in Chapter 6 is 6-9, and that's called Similar Figures. And similar figures are going to rely heavily on the use of ratios, specifically proportions using ratios. So that's where the division from Chapter 6 is going to fit in there. Similar figures are defined as a figure that is either expanded or shrunk, and that's my definition. Okay, so we can look at this square. So I have this square here, and I can go ahead and resize it. So I'm shrinking it, or I'm expanding it. Okay, so I just copied this square. So a similar figure to my original would be this one, which I have expanded. Or this one that I have shrunk. Okay, so that's what you can think of as similar figures. The big idea is that it's the same shape, but a different size. Some specifics about similar figures are that the matching angles are equal. And another quality about similar figures are that matching sides are in proportion. And remember, proportion means an equal fraction, so we're going to talk specifically about having equal ratios. Okay, and I'll do an example to show you this. Alright, so I'm going to draw a couple triangles. And I'm going to say that this angle is 25, this angle is 95. So then, since there's 180 degrees in a triangle, this one would have to be 60. So matching up the same angles, that would mean this has to be 25, this has to be 95, and this would have to be 60. Alright, so that takes care of number 1. Matching angles are equal. So again, by matching, I mean the ones that match up. Okay? And then matching sides are in proportion or have equal ratios. So maybe this is 1, this is 2.5, and this is 6. And I know that this is 2. So again, these are my matching sides. So the ratio here is 1/2. That's going to have to be equal to whatever 6 over whatever this side is, which would also have to be equal to 2.5 and whatever this is. Okay, again. Okay, so if I know 1 to 2, this one would have to be 6 to 12 because I doubled it. And this would have to be 2.5 to 5, again because I doubled it. Okay, so they all have to be equal ratios, half, half, and half. Okay? We're going to look at example 1 in your book. Apparently I can't get those to delete. Oh. There we go. So they're not still on my screen. There. Okay, so that we can see example 1. The two quadrilaterals below are similar. Because it's telling us they are similar, we know that the matching angles are going to be the same and the matching sides or corresponding sides are going to be with the same ratio. Okay? And I want to find the length of CD. So right here. Okay? So I can see right now that BC is the matching side with KL and CD is the matching side with LM. So I'm going to write a proportion. Okay? So I'm going to go ahead and write, well, 2 matches with 3.2, and that has to be equal with X matching up with 4. Okay? So 2 matches with 3.2, X matches with 4. So now I know that I can just solve this proportion by cross multiplying. So that's going to be 8 equals 3.2x. 8 divided by 3.2 tells me that x is 2.5. So that's my answer to what is the distance or the length of CD. Does that make sense? I definitely think that makes sense. Okay? This is cool because we could figure out what the length or the height of something is using shadows. Okay, so we have this scenario here, and we have this flagpole that we have no means to measure it, but we know it has a 72-foot shadow that we did measure. Okay, I also have a yardstick, same time of day, so 3 feet, and that created a 4-foot shadow. These are now similar triangles. So we could use a proportion to figure out how tall the flagpole is without actually having to measure it. This is actually example 2. Okay, so I'm going to match up the sides. 3 matches with H, and 4 matches with 72. So again, I could cross multiply. Then divide by 4. So it's telling me that the flagpole is 54 feet. Does that make sense? Certainly. Okay? So the big idea here is if they're similar figures, you can match up sides and write a proportion to solve, and the angles will always be equal.